Hi guys, I'm back at my desk. It's just before 10 p.m. on Tuesday night, and I think I've put together exercise 13 so that you'll feel a little more satisfied when you watch this with how it went. It was a little chaotic, and I've kind of lined things up for you so that this inference, connecting the inferential piece to the confidence intervals, will make more sense. So without further ado, what you're seeing on the screen, what you'll see on the screen is exercise 13. I've moved things around. They're there for you to see. Hopefully it makes sense for you. So just revisiting what we did. We started with, and let me just make space here. So we started with, here we go, flipping one coin 6 times. Each flip is recorded in this first space here. Then, so I did that, I continued on. So here are my recordings on with my handwriting, and what I ended up with is a sample mean of 3.5 and a sample standard deviation of 1.3784. And then what we did from that is we went to, I had all of you, if you remember, you entered your data into this crazy chart where you put your mean, standard deviation, your X bar. So each of you came up with an individual X bar, which is the mean of the 6 results for number of heads. And then you calculated lower bound and upper bound using the following Excel calculator. If you'll notice in the bottom of the calculator, there's also confidence interval for one proportion. So confidence interval for one mean, practical significance for 2 means, so on and so on. So this is something that we'll use. You save it, we'll use it for in other courses. Actually, no, you'll use this for this course further on. Anyway, now, so you enter your X bar, your particular X bar. In this yellow spot, you enter the sample standard deviation, which I did, and you enter the sample size, which was 6 because you flipped the coin 6 times, and it spits out this lower bound and upper bound. And if you remember, if you click on the T here, I'm producing a value for the 95% confidence interval. The complement is 5%, so 0.095. Complement is 0.05. If I wanted a 99% confidence interval, I would just change that to a 1, which changes, you'll see the T gets wider, and we'll get back to that in 1 sec. So let's switch that back to 0.05. And what we looked at is the idea of, from Lindsay, of the confidence interval sandwich. Does this capture the true population mean? And my lower bound and upper bound captures the 3, which is the true population mean. So I've plotted all of your values on here. So you came up with these, and these ones that are highlighted in yellow are the ones that were missed. So that's where the sandwich missed the jam, as we say, right? And so I've plotted each one of these. I took the time, and you can see those 3 values that missed. So the lower bound here is above 3, lower bound is above 3, and here the upper bound is below 3. So these 3 values. So these are all in order. You can look for your individual value there. Lower bound and upper bound there. The prediction was that 95% of the confidence intervals will capture the true population mean in our case, which means 5% will miss. And in our case, I didn't recount them, so I don't know if we actually had 50. I think we did, or it's very close. So we had 6%. That's an estimate. So it was very close to 5% as predicted by the central limit theorem. So let's go through those again. So again, I gave you at first a bunch of theory. I probably spent too much time on that, which is why everything was a bit rushed. Random sampling is part of the fundamental concept of statistics. When you're making an inference, You need to make, so we're getting back to the inference. That's the piece I think was left a little bit weak. Random sampling you need. Every time you take a sample, there's a little bit of error. When you take repeated samples, you will eventually produce a distribution of sample means, which has specific characteristics. And then we have the central limit theorem predictions. So what I've done for you is on this page, again, it's under the content library, in-class exercises, exercise 13 from 4 concepts to confidence intervals. I put the data set so you can play around with it yourself. So this data set is all these values of the sample means entered in. And I've basically taken a screenshot of those so you can see the list. Now, and then we produce, so the central limit theorem prediction, here it is here, let me zoom in. If the well actually that's not even actually, it doesn't have to be, well actually all it says, if the population from which it doesn't say it has to be normal distribution, so that one is correct. If the population has mean mu, this is the raw scores, and standard deviation sigma, then the distribution of sample means will have mean mu, and standard error sigma over root n. And that is the prediction that was made. When we took your sample means, so I didn't include mine in the data set. So in this data set, all of these individual sample means, and you can see there's a lot of error, so the prediction that there's error is true. Each of your flips of the coins were random. That was not some sort of a setup, unless you guys didn't tell me the truth. Then the prediction was that the population mean of the distribution, the mean of the distribution of sample means would be the same as the population mean. It came out to be really, really close to 3. The histogram is more or less a normal distribution, though it's not perfect. It's more or less a normal distribution. And so the central limit theorem did its job in predicting that. Now, what do we do with that? That is the part that I want to add to this. So we're at 8 minutes, and I'm just getting to the important stuff. So that's a nice result. It showed the central limit theorem at works, but the problem at hand was to make an inference from sample to population. So there's a few little mathematical tricks that I want to get to make this absolutely rock solid. We said we started with this notion that mu is going to be estimated by the sample mean plus or minus a little bit of error. So that's important. Keep that in the back of your mind. Missing links. Missing links. Your sample is 1 out of a gazillion possible samples. Keep that in mind. 2, that's part of this distribution of sample means. Your sample mean is 1 of a gazillion possible sample means. And it's from, think about it as from the distribution of sample means now. So now instead of taking and doing the flipping of the coin, you have a distribution of sample means, and yours is just 1 of the gazillion possible ones. Now, it is a fact that the distribution of sample means is normal with the mean equals mu, which in this case is 3. Let me get the pen. Right? And the standard deviation S over root n. Oh, actually, the prediction was that it would be sigma, right? Sorry. Sigma over root n. Now, so that is important. The next piece that's really important that I talked about, but it was kind of a little bit disconnected, is that it's also a fact that 95%, so in this distribution, this is now, think of this thing here as the distribution of sample means. So the purple area is the gazillion sample means. Each dot, right? So each of those, right? There's a gazillion dots here. Each of those is a separate sample mean, right? Imagine that, right? And 95% of the total area is purple, meaning within 1.96 standard deviations. That is a normal distribution fact. But we're now thinking the key shift that I want you to do is to make it that you're thinking of it as not raw scores, but as sample means. So each of those sample means is one less than or equal to 1.96 standard deviations from the true population mean. So now you're just pulling out sample means one at a time. Okay, so yours was, imagine it just being you drawing one sample mean rather than doing the actual flipping of the coins. Now, we're going to add in a little bit of algebra. But just to make the link for you, you don't need to know this. So if you want to skip through this in the video, feel free to do so. So the raw distribution, the z-score formula was z equals, so this is in the raw distribution. Z equals x minus mu or sigma. You know that. Now, in the distribution of sample means, z equals x bar, because those are the individual elements, minus mu over, and this is the standard deviation, s over root n. So that's just a fact. Now, what do we do with that? Well, if you multiply both sides by s over root n, right, times s over root n, so you see what I'm doing. I'm kind of just doing the basic solving an equation. So I can move, there's a few steps here, I can move from this to this. And what does this look like? Well, gee, it looks like this thing here, right? Mu equals x bar plus or minus error. Mu equals x bar minus z. That's the error bit. So now we have a way of calculating the error, which has to do with the normal distribution and a sample mean from the distribution of sample means. So that fits together. So this fits nicely mathematically, and it doesn't require this some really crazy sophisticated mathematics. Now, so we have a little bit of confidence added to the notion, but there's a problem, and this is what I talked about. The problem is that, well, we have different distributions. So this 95%, so sorry, the black is, right? So that's 95%, but you can see that if you do the purple one, it goes a little bit further out. The 95% goes a little further out, and the red one a little further out. So the degrees of freedom, right? Now the degrees of freedom equals n minus 1. That's an important piece I missed as well. So when you're seeing these DFs all over the place, you're like, whoa, you didn't mention DFs. So it's a sample size minus 1. And I'm not going to go into the math or the reasons for that. Sample size minus 1. Because you really don't need to do it. Remember that when you're doing the Excel calculator, you're putting in the sample size, and when it does the calculations, when it does here, it's doing this T inverse is already taken care of, right? And what you'll see here, actually, if you look B6 minus 1. So I've put that into the formula. So that is the degrees of freedom. It's already subtracting that 1. Okay? So the degrees of freedom n minus 1 is taken care of by Excel. You don't have to worry about it. Now, so we know 95% confidence means 19 times out of 20 you're right. 5% you're wrong. You see where it comes from because you're taking a sample. You want to get something in the purple zone. You don't want to get something in what I call the weird zone, out in the extremities. So we started with mu equals x bar plus confidence times error. We went to x bar plus z score. And then finally, we end up with x bar plus or minus t times s over root n as the formula for the confidence interval. And that is what the Excel calculator is using. If you look at the formula here, if you hold it over the lower bound, you're subtracting that. So again, I'm not sure how much Excel you guys know, but this is basically just a straightforward equation. And it's this equation put into a logical format. Okay, we're at 15 minutes. Thank you for watching, and have a great week.